Okay, hello everyone. And today we are going to discuss the topic of regression. We'll go through definitions. We will discuss the line fitting using the cost function of the least square and squares errors. And we will calculate the R square, which is a measurement of the wellness of the line fitting. We'll try to do the fitting in analytically, and we will discuss outlier data. Okay. Now let's do a quick introduction of what we are going to do here. And so on, we'll use an example here. Um, So suppose, for instance, we have, let me get my laser pointer here. Um, Suppose that we have a data of student grades, right? So these are the student grades um, with respect to their study hours. Now, this is an example, not necessarily the true example. So if the student studies this much of time, then the grade of the students will be this much. Um, 1 hour, 4 out of, I don't know, 14 or whatever. And okay, so we gathered this data from several students. So really, this is a grade versus study hours, as you can see plot. So from this data, we want to predict, and this is why regression is considered supervised learning, because we are predicting from a data that we train the model with. So we go through the training first, and then we do the next is the prediction step. So we want to predict predict the grade of the student um, who studies 2.5 hours. And obviously, if you look at the scale here, this 2.5 hours is not shown here as a sample data point. I don't have this data point. But I need to do a model here to fit this, right? And then I say, okay, well, 2.4, 2.5 hours of the study, that corresponds to grade 6. So from this data, we want to predict the grade of the student. And answer to do that, we have to do really regression analysis or line fitting. Okay. All right. Now, to predict the grade of a student who's 2.5, what we will do, as we mentioned in the earlier slide, we'll do this line regression or line fitting. We'll try to find the best fitting line. All right, this is in the black color. So now once we do that, and that will take a process from us, okay? Once we do that and done, and to look at the graph and says, okay, we want 2.5, which is not a data from the original data, that corresponds to this much of a grade, which is 6.3. So the key here really is to perform this regression. Okay. All right. Given these data, the red dots here, right? How can I perform the best fitting line? That's really the question. So let's go through some definition. Regression analysis is estimating the relationships between dependent variable, okay, dependent variable. And so in the previous slide, the dependent variable was what? It was the grade. and one or more independent variables. In the previous slide, the independent variable was the study hour. So here we go. This is the dependent variable, which depends on independent variable, which is the study hour. The grades, the grade depends on the study hour. The grade is dependent variable, and the study hours are the independent variable. So let's go through the definition one more time. Regression analysis is estimating the relationships between dependent variable and one or more independent variables. So the dependent variable is often called the outcome or the response. Okay, so you can see that in other textbooks or lectures. Independent variables often called predictors, predictors, covariants, features, explanatory variables. Okay, so these are the kind of names or terminology you might see people using in regression analysis. The regression analysis had different types. The important ones are linear regression and the nonlinear regression. And the linear regression computes the line that most closely fits the data, and the model is really linear in its parameters. Okay, we will cover in this lecture the simple linear regression, and there is the multiple linear regression. So the simple linear regression, basically you have one independent variable, exactly like in this case, in this example I have one independent variable. I can have more than, so there will be a third axis here, and independent variables, and I can do two independent variables. For example, the grade depends on the study hours, for instance, and the say for instance the residential location. Okay, we seem to have smart folks live in certain area of the city. Oh, that's kind of odd, but let's just say it's the case. So now you have two independent variables, and now this becomes, as we have indicated here, a multiple linear regression. Okay, you have multiple independent variables. Now, the linear regression. So the other type is nonlinear regression. We are not going to discuss this in our class. This is more of advanced topic for those who are interested. So you can look it up in the references for this topic. So we talked about in this slide, we talked about we need to find the best fitting line. So let's see what does that mean, the best fitting line. Okay, so now obviously this line, when we create a line or find the best line fitting. So a simple linear equation says that y, the dependent variable, equals a, which is the slope, times x, which is the independent variable, plus b, which is the intercept. Okay, so the best fit, it optimizes the values of a and b, that reduces a cost function, and we'll see what is a cost function. And we know that in any optimization technique, method, algorithm, um, you have a cost function, which is kind of your guidance or to the optimization. So in here we will use the square errors as guidance, and we'll talk of them. The squared errors, we'll talk about them in a second. So the sum of the squared errors is my cost function that I need to minimize. So, and obviously, if I want to do a best line fitting here, I'll try multiple ones as it shows here until I find the best line that really kind of optimize A and B. And we'll do that analytically in in very few slides. But this is really the process in a linear equation, simple linear equation where you have just one independent variable. You are just optimizing the slope and the intercept. Okay, so let's talk more now, more depth into fitting a line using the least square. So we talked about a cost function, right? So when I have this line, right? Now, obviously, I'm trying to find how good is this line. So one way to do is to measure these distances between my training data, my original data, to the line. This is called the error or the residual. Some people use that term. Okay, so this distance here is the error or the residual between the point that this line would predict for the xi data. So this for this xi data, this line says that I should be here. But in fact, my training data, my original data says, no, the value should be here. This is an error. An error in what? In the line that I'm trying to use to estimate the data. Okay, so one method to select the line with the least square errors. So least square errors means what? I am going to add the square of the error, this one plus 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 this one, and the sum of this becomes my cost function, and my objective is to find a line with minimal cost function. So the squared error of for point xi, yi, any point, all right, with respect to this line is computed as such. So let's suppose, for example, right, I have this data from my training data. So when I use this as my line to model this data for to use it as the best fitting line, then there will be an error. How can I compute this? Well, I compute this by computing the data here, right? I have the line equation. I multiply the slope times the xi. Where's the xi? Well, here's the xi right here, right? So that gives me, plus the intercept, that gives me this point here, minus, right, the value, minus the yi, which is what the model, what the original data has. It says that when you are at xi, you really should be here, but the model or the line says that I'm fitting, using for fitting, says that here. This distance, okay, is my error. I square it, it becomes my square error. So it is important to understand that we are dealing with two things here. We are dealing with the value that the line is predicting, which is right here, and we are dealing with the value that the data, the training data that I have, is says I'm supposed to be right here, given that I am in xi. All right. The difference is the error. So the sum of the squared errors, okay, so I have this square error for this point, I add it to the square error for this point, to this point, to this point, etc. The sum of the square errors is the sum of the square errors for all the data points. And the best fit is the line that has the least square errors. So the sum of the square errors becomes my cost function that I need to minimize. So the best line is the line with the least cost function with the least squared errors. So this is the squared errors, and sometimes for short we say squares. So this is squared errors, and sometimes for we refer to them as squares. Okay, the squared errors, squares. Okay, so so as I try different lines, right? I'm gonna try different. So I come to this data back again here, and I say, okay, let's try this line, let's try this line, let's try this line, let's try this line. As I try graphically different lines, I will come up with different value for the cost function, okay? And then I will determine the least, okay, the least value of the cost function. That will be my best line. So how to find it? Just if you're doing this graphically, so we trying different values of a, the slope, and b, the intercept. um, this is really sometimes used for large data sets. I would recommend that you really have experience with this before you try to adapt it as your preferred solution. So because you really need to know what you are doing, otherwise you will be spending infinite amount of time trying to fit this curve. But once you get your hand on it, it becomes very straightforward. So the idea really is changing the values of A and B and computing the cost function here. So this is graphically, okay? This is graphically, and you can do the same stuff analytically, okay? So we will do two solutions, step-by-step solution, and this is good for a small number of points. And then we will provide a general solution where you can use for data points. Okay, so let's take a look here and discuss the small the step-by-step solution. Now, before we get to that, we have to talk about a metric that we use. They call it the R square, which is the quality of regression, the regression model. So the R square is a measure of how well a linear regression model. So we have the cost function. That's good and that's cool. But there is a a more acceptable measure of wellness of the model in statistics called R square. So R square indicates the proportion of the variation of the dependent variable that is predictable by the independent variable. In other words, how good my model is. That's what it means. The proportion of the variation in the independent variable that is predictable by the independent variable. That means how well my linear model is. So the R square metric here is between 0 and 1. The closer you get with your metric to 1, it means your model explains the variability in Y, which means it's good. It's good. You have really a very good model. But if it is close to 0, it means that the model cannot explain any variability in Y, which means your model is bad. Okay, so we want to be around as close to 1 as we can, because this indicates your model really has measured the variation of the dependent variable very well. You are able to predict your model is able to predict Y, basically. Now, so how do we calculate the R square? So the R square basically, this is the equation here for the R square, and we want to talk about variation, the variation around the mean, and the variation around the fit. Okay, so the sum of squares around the mean, right? Because we want to compute the variance around the mean. Did I say variation? I'm sorry, variance around the mean and variance around the fit. Oh, I mispronounced that. So we want to compute the variance around the mean. How do I do that? We'll have some math equations here. Bear with me. We will go through numerical example as I always do in my lectures. But we have to introduce sometimes these equations, a little bit of the numerical examples to prepare ourselves for the numerical examples. So bear with me here for a few seconds. So the sum of squares around the mean is defined as the sum square around the mean is that we subtract the mean of the y. Okay, so how do we compute that? Well, we go to all the the y coordinates for the points, add them, divide by their number, and we get their average. Now, I have to find how spread the y's on the y-axis, how spread these y coordinates on the y-axis. And the way to do it is to subtract every y value from the average y, square it, and add it. Okay. If you divide those by n, then you get the variance around the mean. N here is the number of the data points. We are assuming, by the way, population analysis as opposed to sample analysis. And you know that impact which number I divide here, n or n minus 1. Then we want to compute the variance around the fit. So for that, we compute the sum of squares around the least fit. Okay, so to do that, we subtract the data, right? The y coordinate to be specific, and how and the predictions from the line for each and every point. And to be honest, what we are doing here, just to do it graphically, we are just measuring this yellow line here, okay, with this equation. So don't be intimidated with this. Okay, we square it, okay, and then when we divide this value by n, we get the variance around the fit. Okay, so this is basically this value. Now, R squared is computed by the variance around the mean, which is this one here, minus the variance around the fit, which is this one here, divided by the variance around the mean. You do some math manipulation, it's really 1 minus the sum of squares around the fit over the sum of squares around the mean. So you can see that this term, when it gets closer to 0, it means that really your sum of squares um, around the fit are much smaller than the sum of squares around the mean. Okay, so it indicates that you are really getting a good fit here. So this is becomes a small quantity, and then this becomes closer to 1. R squared becomes closer to 1. Now, if you have the opposite, where you have the sum squares around the fit much larger than the sum square, or not much larger, close to the sum of squares around the mean, then and this term gets close to 0. In fact, your model is bad. If you get, by the way, R square into negative, it means that you are getting opposite of the trend. Your line is not only bad but also trending in the opposite way, which is, yeah, you don't want to consider that at all as a fit. Okay, so let's go to an example here, a numerical example to illustrate all of this math stuff. So we will use this example here. I have 3 points, right? 1, 2, 3. And this is their coordinate. X coordinate 1, y coordinate 4. Second point, x coordinate 3, y coordinate 6. Third point, x coordinate 5, and y coordinate is 3. So we desire to compute the best fitting line, okay, obviously, because the number of points is small. We could use mathematical analysis, all right, and that's what we call the step by step. I referred to it in an earlier slide. So we could do this because I have number of points are small because I'm gonna play with equations here. And basically what we'll do, we're gonna assume that we find a line here, which is this one here, which is ax plus b. In fact, this is the linear equation. We didn't find it, but we say that this is the line here. And I'm kind of just telling you that the slope here has a value of a, which we would need to determine, and the intercept has a value of b, which we need to determine. So we want to find a and b that minimizes the cost function or the sum of squared errors or the sum of the squares. So let's go and find the optimum A and B. Okay, so we're going to go through these steps. We'll compute the cost function. And so we will sum all these squares. Then we'll take derivative of the cost function, which or the loss here function with respect to A. Now that's an interesting thing, the loss. So we'll use this in a lot in the neural network, the loss. So what's the loss here? So basically these are the differences. It's this squared errors. The differences between what the model is predicting and what the data is telling me, right? So take the difference and square it. Cost function, lost, all these terms mean the same thing. Okay, so now I want to solve for a, so I take the derivative of L with respect to a equate to 0, the derivative of L with respect to b equate to 0, solve these equations and come up with a and b. And so let's do this. So step one, let's go through step one here. So step one says we want to compute the squares, the cost function, the loss. And this is done by what? You subtract the y coordinate from the equation of the linear equation, assuming that you are using the x coordinate, which is 1 here. Okay, so notice this 4 minus 1 times a, well, 1 because for this point, the x coordinate is 1, the y coordinate is 4. So 4 minus, open bracket, 1 times a plus b. Square that. Okay, let's go to the second point. 6y6 because the y coordinate is 6. Minus, okay, 3y3 because the x coordinate is 3. 3 times a plus b. Square that. Plus 12y12 because the third point, the y coordinate is 12. 12 minus 5 times a plus b, square that. So now this is my cost function, my loss function, my sum of squares. Let's now take the derivative of this function right here, because obviously this function has two variables, a, the slope, b, the intercept. So let's take the derivative with respect to a. So when we derive that, we get this equation. Now, obviously, I have two variables. And let's take the derivative with respect to v, and we derive that. We get an equation with two variables. Two equations, two linear equations, two variables. I can solve that system, right? I can solve this linear system, and I can come up with the values of a and b. So this is solve for a and b. A equals 12, b equals 4 over 3, and this becomes my linear model. Y equals a, which is 2 times x, plus the b, the intercept, 4 over 3, and this is exactly this line here, the black line that you see right here, and this is actually the best fitting line. Okay, so we did all of that using these steps, right? And this is the step-by-step computation. If you have small numbers and you want to go through the process and convince yourself we are doing the right thing. Now, so let's go for general solution. Okay, so obviously I have 200 points, 100 points, etc. How can I do this? Well, the way for linear regression, we need to compute two terms. Okay, so suppose you have n points, you have to compute the sum of cross variations of x and y, and you have to compute the sum of a squared variation of x. The sum of a sum of cross variation of x and y is computed as such by multiplying the x coordinate times the y coordinate after taking the average of from the y coordinate and the x coordinate. Okay, so you compute the average for all the x coordinates and the average for all the y coordinates. You take it out of the data, and this is basically what you are doing. You're doing standardization for the data. Then you multiplying the x coordinate with the y coordinate for every point, and then you sum it. Okay, there's a much simpler term here where you multiply all the x coordinates by the y coordinate minus you multiply n number of points times the average of the x coordinate with the average of the y coordinate. We will compute those in a second, but just bear with me. Now, the second term, which is the sum of squared variations of x, and this is computed by subtracting by squaring all these centered points, right? So these are really centered points. All the we square all the 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 x coordinates of the centered points, right? And add them, and this is equal to multiplying the x coordinate of the original data, square them, and then subtract n times the square of the averaged x coordinates. Now, once we compute these two terms, then the slope is equal to the sum of cross variation of x and y divided by the sum of the squared variation of x. Okay, and the b equals the average y coordinate minus the slope times the average of the x coordinate. So let's take a numerical example here. So let's go back to our original example here. We have 3 points here, right? 3 points, and we want to find the best fitting line using the general formula here. So what we do here is that we compute the SSXY here with this equation. So I find so for example the average x coordinate. So how I do that? Add 1 plus 3 plus 5. So 1 plus 3, that's 4, plus 5, that's 9. Divide by 3. So this average becomes 3. So I subtract 3 from all the x coordinates. This gives me what? It gives me new coordinates, right? But I remove the average. In reality, what I'm doing, by the way, I'm moving all these points to the center, removing the biases from them. And also similarly here, I find the average for the y, 4 plus 6 plus 12, and then divide by 3, and that gives me the average for the y. Then for every point, now I call the new points are the center points. When I remove these averages, I call them the center points. You multiply for the new points, the x coordinate times the y coordinate for every single point and add. Or you can use this alternative formula. At any rate, the SSXY will equal 16. And similarly, the SSXX will equals to 8. Now, to compute the slope here, you divide SSXY over SSXX, and this is 16 times a divided by 8, then equals 2. And then we substitute with the formula where b equals the average of the y coordinates minus slope times the average of the x coordinates, and this comes up to 1 1 1/3. And the values of a and b here matches what we found in the step-by-step solution. So watch here, a equal 2 and b equal 4/3, and this is the same solution we got here when we applied the general formula. Now, one might think of measuring the R square, which is a good a good indicator of how well our data is. So let's measure these, or let's compute these averages. So the average for the y, as we indicated in the previous slide, 4 plus 6 plus 12 divided by 3, that gives you 22 over 3. All right, and then an SS mean equals the square of all these y coordinates for the centered points. So you see how we remove the average, which is 22. This is the average here. We remove it from all the y coordinates, and then we square the y coordinates, and then we add them. That gives me the SS mean. Okay, so this is the comes up to 104 over 3, and then we compute the same SS for a fit, but now instead of using the y average, I use the value that I get from the line. So I fit these values, take the x coordinate, apply it into the linear equation that I got. I get 10 over 3. Okay, so 4 minus whatever I get from the linear equation, square it, plus the 6 here. Okay, so the y from the 6 minus whatever I get from the linear equation using the coordinate 3 for the x, and then 12, the y coordinate for the third point, minus whatever I get from the linear equation using x equal 5. You square it, you add all these three, you get 8 over 3. And then the r squared now becomes just evaluating this formula, and you get 0.9231, which is really a very good fit. Okay, we are very, very close to 1. Okay, so if you go back here, and what we said was that if we have number close to 1, it means that I have a good model. My model really predicting very well the why. Okay, so this it's really a good model. Okay, so now you can extend this analysis of one variable to multiple variables, right? In a linear system. So you can have x1 and x2, and these are the independent variables, right? And and also you can have so so the presented discussion covered simple linear regression, one predictor, okay, which is the independent variable. You can have multiple linear regression models include 2 or 3 predictors, multiple variables. Instead of just x, you can have x1 and x2 and x3, multiple independent variables. And then this becomes your and actually you can have multiple uh dependent variables, not just y. You can have y1 and y2 and y3. Okay, so multiple outcomes, multiple results. Okay, so this is multiple linear regression model. We are really not going to cover that, but just from perspective of FYI. Now, I'm going to conclude with this one simple topic here. It that might not be really very correlated, but just to since we are talking about fitting a line, suppose you are fitting this data, right? Then you have this odd point here sitting in nowhere. So this looks very funny here, standing alone here, not surrounded by data. It's actually off the herd here. So eh, kind of suspicious, right? So this kind of takes us to the data, which is outlier. Okay, so an outlier is a data point in a data set that is distance from all other points, lies outside the overall distribution of the data set, behaves differently, right, from the combination or collection of the data. Very important for when you are doing data collection and data curation, and that's really key thing to weed out any suspicious data. So outlier data, it could be genuine, but it could be also caused by data entry error or experimental error. Okay, it could be sampling error. It could be natural variation due to abnormal conditions, etc. So it really impact my analysis. It causes significant error if it is not genuine. It causes significant error in computation of mean and standard deviation and statistical models, etc. So I have to make sure I get rid of them or investigate them, and if they are false, just get rid of them. So one technique to find out those outlier, there are multiple methods to identify outliers. One of them is the z-score. Okay, and this is the simple, very simple method. So the z-score really measures the distance in standard deviation between a point and the population mean. Okay, so basically for every data point that you process, okay, you subtract the mean from that point and divide by the standard deviation. So obviously it means that you have gone through your data set, you measured the mean and the standard deviation, computed it, right? Then you go back one more time, and for every point you compute the z point or the z score, sorry. In a normal distribution, right? The z-score of 0 equals the mean. So if you have data which is lies right at the mean, its z-score is 1. But and then 68% of the data points lie between plus or minus the standard deviation, which means and now I'm assuming normal distribution. Keep that in mind. Um, so there will be data here and data here around the mean, and if I am between a z-score of 1 and -1, then 68% of my data is here. Now, if I am looking at data between -2 standard deviation and 2 standard deviation of this score, because this axis is the score, by the way, it's labeled by the score, then 95% of the data points lies here from this green, yellow, yellow, green. Now, if I'm looking at data which is from -3 standard deviation to 3 standard deviation, I'm sorry, -3 z-score to 3 z-score, okay, which means add this dark green, light green, yellow, yellow, light green, dark green area, then you really have 99.7 percent of the data. Now, if you have anything outside z-score of 3, -3, or then these are really kind of odd points, right? Um, so, in fact, in our assignments, we will use the z-score of greater than or equal 2. Okay, so we'll start investigating things, even if I'm outside the light green area. Okay, so we will accept the yellow, yellow, light green, but outside that, we have to investigate it or consider it straight as an outlier. Okay, so it is really, as you can see, this is a measure of how to consider data as suspicious. Now somebody will say, okay, so what do we do with the data that we consider an outlier or is flagged as an outlier? What do we do? Well, if you have a small set of data, you might want to consider investigating the cause of it or what had happened. But more likely than not, people are processing lots and lots of data, terabytes, and you're really investigating every single score or every single point might not be practical in these cases. And so you want to just take a very simple approach and say, for that data point, bye bye, you take it out. Okay, so it depends on really the size of your data, the resources available to you, And if you have the luxury of going back and measuring or sampling new points. So this is what about all about what I want to say in linear regression. I hope you have enjoyed it. We obviously have looked at the predictor, linear predictor. There are multiple methods. We looked at the graphical method and step-by-step method and a general method. I hope it was useful to you. And thank you very much. We'll see you in other lecture. Bye bye.